Good morning. It's great to be here. We are going to talk about one of the major work streams, one of the sub-projects within OCP. As you guys know, OCP is the place to integrate a lot of great work from outside technologies. One of the major efforts around OCP integration has been the Composable Memory Systems. Today, with Reddy, I'm here to report on a lot of good work that's been already done within the OCP community. We are part of the server project that is under OCP work groups. So we will cover a little bit of history of Composable Memory System and the journey we have gone through to get to this point, and there are a lot of wonderful activities that invite you to participate. As I said, one of the technologies available to the community has been interconnect technologies such as PCIe or CXL. And the team took a look at the technology that's available and decided that composable memory system is a type of things that a lot of people were interested in. A group of people got together and came up with use cases for CXL as a fabric interconnect technology, and eventually arrived at a number of work groups and use cases that define the work that we want to do. And when you challenge smart people, they normally come up with very good results. And some of the work that we have to do will integrate with effort outside of OCP. The team a minute ago talked about server Reddy, for example, from ARM, or DMTF that we have, CXL, JEDEC, PCI SIG. A number of different technologies bring solutions that will integrate within OCP community. So one of the concepts that's available to us came from CXL specification enabling disaggregated computing. And then once we disaggregate computing, software guys can get together and reintegrate them, compose them in flexible solutions. For example, CXL offers direct attached CXL controllers to the CPUs or GPUs or accelerators. It offers methodology for a memory controller to have multiple ports, so it can be connected to multiple hosts. Therefore, it provides memory pooling and memory sharing capabilities for efficient data movement and increased utilization of resources. Switch fabrics are possible through PCIe techniques, so we could have much larger systems using multiple layers of CXL switches within a fabric that's defined by, for example, CXL 3.1. And then once we have multiple switches, we can consider a number of leaf nodes, devices that are connected, that can be assigned or reassigned to different processing elements. And of course, as part of large systems, not only usability, serviceability, bandwidth, latency, and reliability are all important factors that the CXL community is defining. So in other words, CXL is not just the physical layer, although it is relying on a well-known PCIe physical layer today, just so that people know how it is and work with it immediately. But it has multiple other layers that the community of software and hardware people are getting together to develop the entire system. So as an example, physical layer can be remapped into UCIe. CXL protocol runs on UCIe, but the rest of the ensemble of work that's being done can be transferred to others' physical layers as well. So again, as I suggested, a number of companies, now we have more than 35 people get together on Fridays, talk about composable systems, and Reddy is leading that group. it is great that we move into that. But ahead of that, I maybe put a little plug on other work streams that are going on within OCP. We have hardware-based solutions around DCMHS. There's data center ready modular hardware systems. And there's another work group that is relating to interconnect, extended connectivity work stream that's based on PCIe and photonics interconnects. And we have hardware management that deals with all aspects of resiliency and security of these modular systems. And then composable memory system is the work stream that we were going to jump into now. Reddy, please.
Thanks, Siamak. I will go through the history of how we started this sub-project within OCP. And then towards the later part of the slides, I will actually talk about I will go through a little bit of technical detail on what we have done so far, predominantly covering the CMS architecture part. And then there are a couple of work streams where I wanted to touch upon what's happening so that you kind of get a theme of what we are focusing this year. Hopefully it will interest you enough for you to actually join the CMS sub-project. CMS, we started this initiative back in 2021, 3 years ago, as part of the FTI initiative. It's called software-defined memory. So the theme was, let's take a look at what we need to do in OCP within the context of software-defined memory, define what the right scope should be. Within a year, we ended up actually graduating into the server sub-project, as Siamak was mentioning. We actually started off with what are the key use cases we should be focusing on for the composable memory. And then how do we actually gather the broader industry, the contributions into OCP. As you can see, last year we had a significant presence in the OCP Global Summit. So quite a number of contributions that actually shaped up. We have one specification which is actually contributed by Google and Meta. It's a CXL memory expander specification for hyperscalers, specifically looking at the requirements for the memory expansion capability. We also delivered 4 white papers. This includes use cases, workloads, memory access tracking, and then obviously the architecture part. So the architecture basically lays the foundation work for what we do within the context of CMS. So we wanted to do something very quick last year. And then of course, almost 15 companies or so actually participated in the OCP. It used to be called Experience Center. So it's basically innovation village, demos. So quite a bit of, interest from the community, significant amount of progress last year. Going into this year, our focus is really looking at, identifying the specific set of use cases that we really want to target. This includes the hyperscaler infrastructure as a service type of use cases that, virtualized, containerized, and bare metal. And then also AI and HPC, the fabric-based use cases as well. So we have 5 work streams that are actually focusing on different facets of the CMS scope this year. These work streams got kicked off probably like maybe 3 months ago, a very early part of this year. So we partitioned the scope into 5 different work streams. So the composable workloads is essentially looking at what are the set of workloads that we really need to focus on to drive composable memory solutions into. And then we have data center memory fabric orchestration. So without having an end-to-end solution, there is not a whole lot you can actually do. So fabric manageability is a very critical component. I will go into the one click down on the fabric manageability architecture. And then AI and HPC systems and fabric, we wanted to have a very specific and dedicated focus for AI side of the workloads. Specifically looking at the fabric and then how do we actually compose the memory for GPU-centric or accelerator-centric type of use cases. And then the computational programming is fairly emerging. Essentially, you probably might have heard about near memory computing, computational storage that SNIA actually was driving, has been driving for quite some time. We needed to do something similar for memory as well. Essentially look at how do we have the compute element closer to memory as opposed to farther away from the memory. So it requires evolving programming models and lots of architecture patterns around it. And the last one is actually we want to have connectivity with the universities and research community as well. So those are the 5 work streams that we currently have in flight. So real quick, the focus for this year for each one of these work streams is composable workloads, define the workloads first, the critical ones specifically. That includes AI HPC as well. And then have case studies around it. So how do you take an element of what Siamak was talking about, direct attached memory expansion capability, multi-ported or pooled or shared type of implementations, and adapt it for specific use cases that can really benefit from. So that's really the goal of case studies. Data center memory fabric orchestration, our goal is to essentially have an architecture spec. This includes the API, stitching together the end-to-end API flows. And then on the AI side, we want to actually have an AI-specific architecture patterns for composable memory, and then have a white paper specification around it. Computational programming, the team is currently focusing on one white paper that essentially talks about why computational programming is very important and go through different programming models. And then we'll probably end up making more focused effort next year. There are foundational contributions that need to happen besides the workstream, targeted focus areas. So the memory expansion capability that I talked about as the base specification that covered only the DDR media. Now, how do we take storage class memory? How do we take NVM and expose that over CXL? What are the key requirements that we need for that type of device that is being exposed through CXL? We need to essentially look at those details and have a specific set of specifications for it. Then we are also looking at more of, if you look at the switching capability that we actually need to work on, there are not many CXL switching vendors out there that are readily available for us to actually build these solutions, build the specifications and white papers. So we are looking at what is the best way for us to expose that through OCP Experience Center locations to see if we can actually do something more interesting for the broader community. So going into the details, high-level logical architecture, it's a very, very high-level cartoon picture. So we look at, there are compute elements. Compute could be CPU-based or GPU-based. And then you essentially have memory. It could be near memory or far memory. So the way we characterize the near memory in the CMS sub-project is anything that is directly reachable, connected to the socket, specific CPU socket, or it is a remote CPU socket, or it is a CXL, memory expansion capability that is basically one NUMA hop away from a latency perspective. It's almost as good as going to the other socket memory. Those are all characterized as near memory. Far memory essentially includes anything that is a little bit more latency oriented, higher latency, and things like CXL buffer behind the CXL switch is one example, right, for the far memory. Clicking down on the logical architecture, so this architecture is supposed to include pretty much the broad spectrum of use cases. So it starts off with direct attached memory expansion functionality, whether it is single or multi-logic devices. And then you have multi-ported devices that are actually that need to be covered as well, where you are essentially connecting not just one host, but multiple hosts. And then you have the fabric-based CXL, pooled solutions, pooled or shared solutions. So we need to include that in the scope. And then the emerging one is really the CXL memory enclosure with alternate transport. We just left it as something that there is cheese down the path, but we have not really focused on that element, and you probably will see some focused efforts, later on, starting this year. Stitching together all these elements is essentially the data center fabric manager, and we need to worry about implementing that end-to-end to be able to say truly composable solution. So here is the workstream focus for the CMS workload, workstream. It's essentially, this team is looking at pretty much broad spectrum of workloads, starting with the general compute. This includes containerized microservices as well as virtual machines. And then you have the storage-centric, analytics-centric, as well as AI and HPC type of workloads. The team is essentially focusing on what are the set of benchmarks, how do you fine-tune the benchmarks, and contribute some software elements to make sure everything is working end-to-end, and have the case studies around it. So here is the data center fabric manager architecture clicked on. What you see is you essentially have the critical component is really the centralized data center memory fabric manager. This needs to actually work in tandem with the CXL-based media that is actually sprinkled across in the data center using the CXL fabric manager agent. It can be in-band agent, it can be out-of-band agent. So out-of-band could be through BMC. In-band is essentially using CXL.io through the host, specific agent-based interaction. Our plan is to have Redfish-based profiles as a starting point for an integration, and then essentially use the CXL-based lower-level constructs, which is essentially the fabric manager APIs, which is CCI-based interface in the switch, to be able to actually stitch together the entire end-to-end solution and make sure we can actually deploy this using Kubernetes framework. So what it means is now you have a full-blown Kubernetes-based memory orchestration that we really want to showcase in the global summit timeframe. This is the work in progress. One of the key contributors in the CMS for the data center memory fabric manager is Jack Abbott's lab. This team is actually working on building a concept POC. We won't have enough time to actually cover this. So currently, they recently posted developed the POC code. So there are two building block elements in this one. One is the command line on the left-hand side, essentially using that as a way to control the switch, the orchestration flows. On the right-hand side, you have the CXL switch emulator, because we don't have working CXL switch with fabric management capability for us to actually do something more interesting. So we are starting off with the emulation capability. So the team actually built an emulator that we currently have the POC code that, to showcase how these end-to-end flows actually work for the data center memory fabric manager. And there are links down for the blog as well as the code that is contributed in the GitHub. I strongly recommend you guys to watch the YouTube link as well. That essentially has the details behind on how the demo actually works in the POC code. The call to action, please do join the CMS project. There is a lot of interesting stuff that is happening in the community. Like I said, there are emerging tactical focus as well as way forward-looking, focus. Computational programming, revolving around the memory is a big deal. So there is quite a bit of interesting stuff. I strongly urge all of you to actually join. We do meet weekly on Fridays, 9 a.m. PST. It's a very lively community. There is a lot of interesting debates and discussions that do happen in these meetings. So I request you to join. If you are looking for additional information, if you go to the OCP CMS wiki folder, you have all the details around it, including the call recordings for the prior calls. Thank you. I guess we have almost 1 minute for Q&A. There are specific questions.
So again, this is a community to get together and get things done. It is a hardware, software, and security and management all co-design. the first aspect of what we've been trying to do is first do no harm. If software expects certain things to work, although hardware changes, our job is to abstract it away, but it takes effort. Zach told us that we can put things together in a PowerPoint and call it done, but it takes many, many people, many, many hours, and perhaps years to get it done right. But at the end, we push the envelope. If it is too hard, we stop and find another way. And we try to put things where they belong. That's why within the OCP community, we have hardware teams do things in a partitioned way, in a modular way. And then we have software and management teams try to put it back together. And we need your help.
All right, thank you.